So we have this 2095 of LeetCode, delete the middle node of the linked list. And the question states that you are given the head of the linked list, delete the middle node and return the head of the modified linked list. The middle node of a linked list of size n is the n by 2th node from the starting using 0th based index. So basically, you will be given a linked list, and you need to delete the middle node and return the head of it. Right now, I'm going to discuss two methods of doing it. One would be the brute force way, and other would be an optimal way by using fast and slow pointer method. This is a specific algo used in linked list problems to minimize the time complexity. So this is going to be roughly of the time complexity. The brute force way would be of n plus n by 2, and this is of the time complexity n by 2, right? Now the main part of the question is this part, the constraint part. This is the main part of a question. Even if you write a correct code, it does not mean it would execute under a time, right? So this part of the question is most important. It says that the number of node in the linked list is of the range from 1 to 10 raised to the power 5. Now if we go over the basics, right? If we go over the basics, if you're writing in LeetCode, right? In LeetCode, if you're using C++, the basics is in 1 second you are allowed to have 10 raised to the power 6 operations, right? In 1 second you are allowed to have 10 raised to the power 6 operations, and you are only given 1 second to execute your code, right? So you are allowed to perform at max 10 raised to the power 6 operations, right? But what you are given here, the value of maximum value of n, let's say you are given a test case, the maximum amount of nodes in a linked list can be 10 raised to the power 5, right? The minimum can be 1 and maximum can be 10 raised to the power 5. By this, just by this information, I would be able to like roughly say the time complexity, the maximum and minimum time complexity that I can put my code into, right? So this, let's say you have a linked list of the uh, number of nodes be 10 raised to the power 5, right? That simply means that a single iteration of on is going to take a time complexity O of 10 raised to the power 5, which is smaller than 10 raised to the power 6, right? Which is smaller than 10 raised to the power 6. So what you can actually see is, if I have a time complexity 10 of n, O 10 of n, this is going to be almost equal to 10 raised to the power 6. So n is 10 raised to the power 5. 10 times 10 raised to the power 5 is going to be 10 raised to the power 6. So our time complexity of the code, time complexity of the code can be of the order from O1, the minimum, to a maximum of O 10 of n. How do I figure out? N, if I am assuming the maximum, that one test case having a number of node to be 10 raised to the power 5, then a single iteration over it will cost me an O(n) time complexity. The n value is 10 raised to the power 5. Now I can go over it. Now it is still less than 10 raised to the power 6, so it is going to execute under a second. Now I can go over this linked list having 10 raised to the power 5 node 10 times and still have time complexity less than 1 second. So I can clearly say the maximum time complexity that I can have is O10n. So I can just by this line, a single line, I figured out I can have a minimum time complexity of O1 and a maximum time complexity of O10n, right? I can also have O n log n. N log n is again smaller than 10n. I can have O log n, O n by 2. Now the thing that I discussed was the brute that I'm going to discuss is the brute force way. The brute force way, the time complexity is of the order O n plus n by 2. Now let's see if sorry. So let's see O n plus n by 2 is lies between this bracket of time complexity, right? O n plus n by 2 is simply O 3 by 2n, right? N plus 1 by 2 is 3 by 2n, which is O 1.5n. O 1.5n. Now O 1.5n is clearly less than O 10n, right? 1.5 is less than 10. So our brute force way is going to be executed under 1 second. And obviously O 0.5n, which is n by 2, the optimal way using a fast and slow pointer is going to execute under O 10n. So basically, both of this brute force way and the optimal way is going to be executed under the time constant. So we are never going to get TLE, right? We're never going to get TLE even if we're using the brute force way. So going on the brute force way, the brute force way is really simple. So let's take an even number of node and an odd number of node to exactly understand. Let's say even number of nodes. Let's take 4 nodes, 1, 2, 3, and 4, right? And odd number of nodes. Let's take 3 nodes. Let's say 5 nodes, 1, 2, 3, 4, and 5, right? Now here the number of node is 4, and here the number of node is 5. Now the first thing, the final thing that I have to do is I need to calculate the middle number of node, which I can do 4 by 2 is 2. So I will start from the beginning, from the head, and jump to step 1, 2, and this will be our middle node that I need to delete. And then if I have a number of node to be 5, then I can calculate middle. 5 divided by 2, 5 divided by that 2, that is 2.5. So in integer it will be 2. So I'll start from here and I will go 2 step forward, and this is the node that I'm going to delete. So in order to delete this node, okay, I need to stop the beginning one step ahead of it, right? So that I can actually break this pointer and switch it to the next pointer. So it will be, if I'm here, right, if my temp is here, somehow I can bring my temp before, just one step before the middle node. So what I can say is that temp next, this is the brute force way that we're discussing. Temp next, this temp next is this arrow, right? This arrow I need to point it to temp next. So temp next, and before pointing it I need to actually remember this node, right? After pointing it I cannot go into this node. So before pointing it I need to remember this node. So I can list node star middle is equal to temp, this is the temp where we stopped, right? Temp next, right? Now we have the middle. After pointing, changing the pointer, simply what we will do is we'll call in C++, we can call delete. In C we can call free function delete a middle, and we'll simply delete the middle node and return the head of it, right? Head of it. And counting is really simple. Counting, simply you will assign the temp in the head initially. Okay, I'm going to write it again. Counting the number of node is the first step. Okay, I'm writing the steps. The first step of solving this kind of problem is simple, right? First count the number of node. You need to know how many node you have, right? So that after that you can go to the middle node. So first count the number of node, and then go to the middle and simply delete the node and return the head is the fourth step. Return the head. You can do this, right? You can delete the node by simply calling delete function. You can go to the middle by simply running a while loop. How you will count the node? Simply write before write a list node, create a pointer, let's say temp, and assign it to head, and write temp. You can simply write temp or temp not equals to null. Create a, and you have to move the temp to the next node. So temp equals to temp next, and increment the counter. Maintain a counter initially at 0 and increment the counter plus plus. You'll be able to count the node. After counting, you have to go one step before middle. So one step before middle, once you calculate the middle as count divided by 2, run a for loop or a while loop. You can simply run a for loop. Let's say for int I is equals to 0, I less than middle minus 1, I plus plus, let's say before running this for loop, you have to set the temp to head, right? And what we did was, again we set the temp to head, and we have to move one step before the middle. Now we have the middle, so we'll simply shift the temp, right? Temp is equals to temp next, and we moved one step before middle, right? And after that, you execute these three lines, and you have your answer, right? This will be a brute force way. So simply you count the number of node, then go to the middle, then delete the middle node by simply performing this three step, and return the head of the linked list, right? This will be the brute force way of solving this problem. Now this is going to take a time complexity. If you calculate this, iterating over the whole linked list is going to take a time complexity of on, right? And this thing of iterating again from starting from the head, moving to the middle of the node, or almost the middle of the node, is going to take a time complexity of on by 2. So together it is going to take a time complexity of n plus n by 2, which is below O10n discussed before. It is never going to give a TLE, and it's going to work, but there is a better way of solving this problem, right? We can actually use a algorithm known as turtle and hare algo, better known as fast and slow pointer. This algo is so simple and so efficient. Like this is really easy to understand. I'm going to keep it really simple. Let's draw 5 nodes, right? If I'm doing for odd nodes, you can do simply for even nodes, right? 2, 3, 4, and 5 nodes, right? Now, this is our head. We need to maintain 2 pointers, right? We need to maintain 2 pointers. One would be our fast pointer, and another would be our slow pointer, right? Now the rule is, we move fast pointer 2 step ahead, and when we move the fast pointers 2 step ahead, we move the slow pointer only by 1 step. So in the first iteration, what we will do is, we'll move our slow pointer 1 step ahead, and we'll move our fast pointer 2 step ahead. Okay, we still did not reach null or the node before that. So again we'll move the slow pointer 1 step ahead, and the fast pointer 2 step ahead, right? Now see, now we cannot move the fast pointer 2 step ahead, right? We cannot go after null. There is nothing after null. So we'll stop here, right? We'll simply stop here. Now, if you clearly see the slow pointer is actually at the middle node, right? We got to the middle node just by iterating O3 times. We actually moved the slow pointer 3 times forward, and we have the middle node without even having to iterate over the whole linked list, right? Now this is for the odd case, right? If you have the odd number of linked list, the odd number of nodes. Now for the even, what you can do is, for even, let's draw 4 nodes, right? 2, 3, 4, and null. Now initially this is your head, this is the slow pointer, and this is the fast pointer. Again the same rule, you move the slow pointer 1 step ahead, and you move the fast pointer 2 step ahead. Still have space, still fast pointer can move 2 step ahead to null, so again move the slow pointer 1 step ahead, and fast pointer 2 step ahead. Now fast pointer cannot move any 2 step ahead, right? There's nothing after null. Null is the ultimate. So if you see the slow pointer, now slow pointer is again at the middle node, right? But there is a little problem here. This is a single linked list, right? You cannot go back. So once you are at the middle node, how you're supposed to delete this node, right? So somehow you have to uh, be at 1 step before the middle node, so that you can delete the middle node, right? What you can actually, the clever way of doing it is, what you can actually do is, I'm doing it for the even and odd case. This will be our even case, and this will be our odd case. Just getting 1 step before the middle node, what you can do is, you can move the fast pointer 2 step ahead once, and then move the slow pointer, right? So we are moving fast and slow pointer together, right? We are moving fast pointer by 2 and slow pointer by 1. So before performing this while loop, why don't you just move fast pointer 2 step before performing this while loop? Then you will actually go 1 step before the middle. Let me demonstrate. Let's say we have 4 nodes. Let's say we have 4 nodes and we have the fast pointer here and slow pointer here. Before into going into the while loop, why don't you just move the fast pointer 2 step ahead and now run the while loop? Now what you do is you move the slow pointer here and the fast pointer here. Now the while loop stops, and if you can clearly see, you have the slow pointer 1 step before the middle. Then you can simply go to the middle node, delete it, and touch and go to right. You can simply do slow next equals to slow next next. You can perform this simple operation to connect this two node, and you will be able to delete this node and have the middle node deleted for the even case. Simply do the same thing for the odd case, right? Let's say you have 5 nodes, 1, 2, 3, 4 and 5, right? And you have null at the end. Now you have the slow pointer here, and fast pointer was initially at the and at the first node. Before running into the while loop, why don't you just move the fast pointer 2 step ahead and then go about moving both the fast and slow pointer by 2 and 1 step. First move the slow pointer by 1 and move the fast pointer by 2 step, right? Now fast pointer cannot move any further slow, so you can, if you look at the slow pointer is actually at 1 step before the middle node. This is our middle node that we need to delete. Simply break this arrow, connect it by writing slow next is equal to slow next next, right? Slow next next, and right delete the middle node, and this middle nodes get deleted and return the head. Simply return the head. This is the most simplest code that you can write, and actually this runs at O(n) by 2 time complexity approximately, right? The brute force way actually worked at O 1.5n, and it actually worked O 0.5n, right? Now writing the code is really simple. Whatever we did here graphically, we are going to write in code, right? The first thing, what is the first thing that we need to check is if we have a single node, or if you have a null, just simply a null, then we'll simply return a null. So first thing that we are going to check is if, right, if head equal to null, if we don't have a linked list, or if head dot next equal to null, right? If any of these case, right, if you have a single node, then this will be the middle node, so deleting this node, you can simply return the null, right? Any of this case, return null. What is the next thing that we did? The next thing that we did was not to get into, see, this was the fast and slow pointer concept, and we actually, let me change the color. This was the fast and slow pointer concept, right? This was the main concept of getting into the middle node. Now actually we modified this fast and slow pointer so that we can get 1 step before the middle node. Now the modified function, in this modified function, what we did was, before even going into while loop of changing fast and slow pointer by 2 step and 1 step, we actually moved the fast pointer 2 step ahead in every single time, irrespective of even an odd case. So do the same thing. First we need to define, right, the fast and slow pointer. So list node fast equal to head. Similarly, list node slow equal to head. Then what we did, before getting into while loop of moving both of this, first we moved the fast pointer by 2. Fast equals to fast next and next, right? Then we are going to have a while loop. Now what should be the, looking at this, what should be the condition at the end, at the ultimate? Either my fast pointer is going to point at null, or it is going to be 1 step before null. So if my first pointer is going to be null or one step before null, so this is going to be our boundary condition, right? So the boundary condition will be while first pointer is not equal to null, or and while the first pointer is not equal to null, or the first next pointer is not equals to null, or and the first next pointer is not equal to null. Now we need to put an AND operation. Why? Because either, let's say for even case, let's say we have two nodes, right? We have two nodes and we have a condition of three nodes. In even node, the first pointer is going to be here, and in the odd node case, the first pointer is going to be here at the end, right? Now the first pointer should not be equal to null, and the first pointer should not be equal to this node. If we put an OR here, let's say if we put an OR here, if this condition is false and this is true, this is going to pass. So we need to make sure that both the condition does not pass. So we need to put an OR, so the both condition is checked. First should not be equal to null, and first next also should not be equal to null, so that we take account of even and odd case, both of this. What we do is we're going to write two lines. What we are doing, we are moving the slow pointer by one step, slow next, and we are moving the fast pointer by two step, fast next and next, right? Now we will be one step before the middle node. Now this is the middle node that we need to delete, right? So before changing the arrows, right, before changing the direction, we need to actually store the middle node into some pointer, so that after that we can delete it. So we are going to create a pointer middle and put slow next into it, slow next into it. So this is our slow pointer. We change the color. So this is our slow pointer, and slow next is this node that we need to delete. This is our slow pointer. Slow next is this node that we need to delete, and this is stored in the middle, right? Now what we are going to do is slow next is equal to slow next next. So this link is created, right? This link is created, and at the end simply delete the middle and return the head. Return the head, and you have a code that actually runs at, this is the simple while loop that runs o(n) by 2 times, and there is no loop other than this. So approximately we can say the time complexity of this code is o(n) by 2, and the space complexity of it is o(1). This is the most efficient use of fast and slow pointer in deleting the middle node of a linked list.